Welcome, Math 111 students, to section 11.1, Systems of Linear Equations in Two Variables. All right, so for this section, we're hoping to learn how to solve systems of equations by graphing, by substitution, by elimination, how to identify inconsistent systems, and how to express the solution of dependent equations. All right, so that's a lot for one section, but let's get started. Actually, I just realized my glasses are kind of funky here, so I'm just going to take 2 seconds and wipe my glasses off here. You can't see me doing it, but it doesn't mean it's not happening. Oh, that's so much better. All right, let's get started. Sorry about that. What is a system of equations? A system of equations is really just a set of equations, and a solution to the system is a solution to all the equations in the set. So if you can find an x and y that solve both these two equations, then that's a solution. So let's look at an example. X equal to 1, y equal to 1 is a solution to this linear system. And we usually write solutions as an ordered pair. And the order tells you which value goes with which. So the x, oops, I got to get a pen. The x is the first value and the y is the second value. So 1, 1 is a solution to the system. And how we would check that is that we would just plug in 1 for x and 1 for y. So in the first equation, it's x plus y is 2. We would write 1 plus 1 is 2. And in the second equation, 2 times 1 plus 3 times 1 equals 5. Both those equations are true, and so 1, 1 is a solution to this system of linear equations. Sometimes it's helpful to look at what isn't a solution. Negative 1, 1 is not a solution, because this time we're going to plug negative 1 in for x and positive 1 in for y. Negative 1 plus 1 is not equal to 2, right? That's 0. 0 is not 2. We don't even need to check the second one. It's not a solution to this linear system because it has to solve all the equations. All right, this system is a linear system of equations since all the equations in it are linear equations. Remember, the graphs are all lines. Not all systems of equations are always linear, but we're going to be working with linear ones in Math 111. All right, so there are 3 types of linear systems, okay? There is an independent system of linear equations. These guys have exactly one solution, and that's this graph right here, the very first graph. This is an independent system. You can see you just have 2 lines. They cross at one point. That's an independent system of equations, and the solution will just be 1 point xy. A couple other things can happen. You could have an inconsistent system of linear equations. These have no solutions because the lines are parallel. So this one right here is your inconsistent system. And you can see there's not going to be any solutions because those lines are never going to cross. So there's never going to be a point on both the blue line and the red line. And the final thing you can have is you could have a dependent system. Well, this happens when you actually are solving a system of linear equations and they both turn out to be the same line. So that means every point on this blue line for the dependent system, oh no, what has happened here? Every point here on the line is a solution to the equation. So whatever the equation of that line is, that's going to be all your list of all your solutions. All right, let's talk about the ways we can solve these guys. There's 3 methods for solving system of linear equations. You can do graphing, substitution, or elimination. We're going to start with graphing. All right, so let's do an example. Here's our system of equations, minus x plus y equals 2, 2x plus 3y equals 6. And we're going to solve this by graphing. And I'm actually going to go ahead and graph these by hand. I'm going to use a method that I just call the intercept method. And so what I do for that is for each of the 2 linear equations, I plug in x equal to 0 and I figure out what y is. I plug y equal to 0 and I figure out what x is, and then I just draw a line between those 2 points. Let me show you an example. So let's look at the first equation, minus x plus y equals 2. So the first thing I'm going to do is I'm going to set x equal to 0 and figure out what y is. This is going to be my y-intercept. So if I plug x equal to 0 in that equation, I just get y equals 2 because minus 0 is 0. So that gives me the point over 0 up to as 1 point on the first line. The next thing I do is I set y equal to 0. That tells me that minus x plus 0 equals 2. So minus x equals 2 or x equals negative 2. So that's the point negative 2, 0. So let me plot those guys. There's the first one, 0, 2. Here's the second one, negative 2, 0. And now I'm just going to draw a line. I really wish this program had a straight line grapher, but I don't think it does. I'm just going to do my best to try and draw a straight line. And maybe I have a ruler here in my office somewhere. Let's see if I can find it. Oh, here's one. I wonder if I can use a ruler on top of a laptop. We're going to find out. All right, let's try and draw a really nice straight line. You guys at home do the same. Try and draw a really nice straight line. Hang on. I want this to look good. Okay, let's see how that's going to look. I don't know. We'll see. Actually, that's not too bad. All right, so there's my first line. So this is what I did in green. All right, oops, that was not good. This one I did in green. All right, let's try the next line. I'm going to switch to purple. All right, my next equation is 2x plus 3y equals 6. I'm going to do the same thing. I'm going to set x equals 0 and solve for y. That means 3y equals 6 or y equals 2. That's the point 0, 2. Well, that's interesting. And now we set y equal to 0. 2x equals 0 plus 0 equals 6. X equals 3. So that's the point 3, 0. So I plot these 2 points, 0, 2. I think we found our intersection point. And 3, 0. And now let's draw this line in. I'm going to fumble around here with my ruler a little bit, try and do a really good job. Actually, I might get one more point. This is 1, 2, 3, 1, 2, 1, 2, 3, 1, 2. Continuing my slope here. Let's see if I can draw a good job for this. I think that's going to be pretty close. Let's try that. There we go. All right, and there's my pink line. And we can see the intersection of these 2 points happens exactly at one point, and that's the point 0, 2 is the intersection point. So 0, 2 is the only point on both lines, and it's the only point that solves both the equations. We can check that 0 plus 2 is 2, and 0 plus 3 times 2 is 6. So there's my solution. All right, we're going to do example 2 using Desmos. If you want to try and graph it by hand, that's great. If not, you can use Desmos to help you. Sometimes it's great to use technology. So let's graph our first line. Our first line is 5x minus 2y equals 4. And here's one thing that I love about Desmos is that in graphing calculators, you have to solve it for y equals. In Desmos, you can just put it in standard form. And let's do 10x minus 4y, minus 4y, shall we? Hello, 4y equals negative 7. And there is that one. And now when we look at these two graphs, we can be like, hey, what's going on here? These guys are never going to cross. Zoom out as far as you want. These guys are parallel lines, and they're never going to cross. And we can see that if we compare the slopes of these two lines are obviously the same slope. If we solve these for slope-intercept form, you could see that the slope is, it looks like it's 5/2, but I'm not totally sure off the top of my head. So you can solve for their slopes and see that they have the same slope. So you write for the answer for this one is that no solution. These guys are the same parallel lines, same slope. All right, so the basic idea of the substitution method is we take one of the equations and solve it for one of its variables. Then we substitute that into the other equation. Let's do an example. All right, we're going to solve this equation by substitution. So the first thing we're going to do is we're going to pick one of the equations and solve it for one of its variables. It doesn't matter which one you pick. You can do either one. It's going to work out the same. I can see that if I look at the second equation, it already is solved for one of my variables. I have that y is equal to 3x. So that one's already kind of set up for me, so I'm going to go ahead and use that. Now I'm going to take that y equals 3x and I'm going to substitute it into equation number 1. So I write x plus, now instead of writing y, I write 3x because y is 3x equals 4. So I used this equation here, but instead of writing y, I wrote 3x. And now I just need to solve this equation for x. X plus 3x equals 4. Well, x plus 3x are like terms, so that's equal to 4x equals 4. Divide both sides by 4, and I get x equals 1. Well, I'm not quite done because I only have the x value, right? And I need x and y values for a solution. So I take this back to my first equation that was solved for one of my variables, and I know that x is 1, so I can figure out what y is. Y equals 3 times 1, so y is 3. And now I write this as an ordered pair, x first, which is 1, y first, which is 3. It's always a good idea to check your answers in both equations when you're solving systems of equations. So let's do a quick check over here. Let's do a quick check. The values 1 and 3. Is 1 plus 3 equal to 4? Yep. is 3 times 1 equal to 3. Yep. So I checked in both of my equations. All right, let's try another example, a little bit trickier one. Here's example 4. Let's solve this by substitution. You can see neither of these two linear equations are already solved for a variable. So we're going to have to pick one and solve it for a variable. I'm just going to pick the first equation, minus x plus y equals 2, and I'm going to solve it for y. You could solve it for x, but I'm just going to solve it for y. Why not? So I'm going to add x to either side of the equation. And that gives me y equals x plus 2. Now I take this and I plug it into equation 2. Everywhere I see a y, I'm going to put in x plus 2. So 2x plus 3, not y, x plus 2, equals 6. Now I solve this equation for x. 2x plus 3x plus 6 equals 6. So 2x plus 3x, those are like terms. I can add them to get 5x. Plus 6 equals 6. Subtract 6 from each side. 5x equals 0. Divide by 5, which is still going to give me x equals 0. I take that back. That's one part of my solution. And I plug that into my equation for y. Y equals 0 plus 2. So therefore y equals 2. And my solution is x equals 0, y equals 2. Now I'm going to check my answer. Let's come over here and do a quick check with both my equations. Minus 0 plus 2 equals 2, check. 2 times 0 plus 3 times 2 equals 6, check. Both those work out, feel good about it. All right, that's the substitution method. Now let's talk about the elimination method. The elimination method is similar to the substitution in that it's an algebraic method. We're not going to be doing any graphing. But in the elimination method, we add the two equations together and we hope that one of the variables drop out. Now to get that to happen, sometimes we have to multiply by a linear factor. Let's show you an example of how this works. Here's my first example. I have one equation. My first equation is minus 2x plus 2y equals 4. And my second equation is 2x plus 3y equals 6. What I can do right off the bat is I'm just going to add these two equations together. Just add them together. And so I'm adding straight down. Minus 2x plus 2x is 0x. Right? 0x plus 2y plus 3y is 5y equals 4 plus 6 is 10. So when I added those two equations, I got 0x, which I don't even have to write, right? I really just got 5y equals 10, which I can solve for y no problem. Y equals 2. Now I know what y equals, so I can come back up here and plug that y value into either of the two equations and solve for x. Let's plug it into the first equation. Minus 2x plus 2 times 2, which is my y value, equals 4. Minus 2x plus 4 equals 4. Subtract 4 from each side. Minus 2x equals 0. Divide by negative 2. X equals 0, y equals 2. So we got the same answer as before, this way by elimination. All right, let's try another elimination problem that's just a little bit trickier. All right, I realized I forgot to put one of my examples in, so I'm just writing this in and I will update the notes and you guys will be able to see this example. So here's the next example I want to try for elimination. All right, you can see from this one, if I tried to add down right away, in fact, let's just go ahead and do that. If I tried to add down right away, nothing good's going to happen here because I get 4x minus y equals negative 13. Well, none of the variables dropped out, so I'm not any better off than I was before. I can't solve this for one of the variables because I still have an x and a y. So that isn't useful right off the bat. So what we can do, though, is we can change one of our linear equations so that something drops out. For example, if I had a negative 3 coefficient on this x, then when I added down the 3x and the negative 3x would cancel. So to make that be a negative 3 coefficient, I'm going to multiply the second equation by negative 3. I'm going to multiply the entire second equation by negative 3. So now my system would be 3x plus 4y equals negative 5, and then negative 3x plus 15y equals positive 24. I took negative 3 times all parts of the equation. Negative 3 times x is negative 3x. Negative 3 times negative 5y is 15y. Negative 3 times negative 8 is positive 24. Now, when I add my equations together, the x's drop out, and I get 19y equals negative 5 plus 24 is 19. Divide both sides by 19, and I get y equals 1. Go back up to one of my original equations, and I solve for x. Let's use the second equation this time. X minus 5 times 1 equals negative 8. X minus 5 equals negative 8. Add 5 to each side, and I get x equals negative 3. So my solution is negative 3, 1. And I can go ahead and check that quickly. Negative 3 minus 5 is negative 8. Negative 9 plus 4 is negative 5. So check, check. All right, let's do one more example of elimination. This one I want you guys to try on your own. So pause the video, give this one a try. We'll come back and go over it. Give it a try. Did things go smoothly? Maybe, maybe not. All right, what do we want to multiply by here to get the one of the variables to drop out? Well, I can see that if this was a negative 5x, then I would be able to solve this equation. So I'm going to multiply equation 2 by negative 5. 5x minus 20y equals negative 40. That's my first equation still. Minus 5x plus 20y equals positive 40. All right, let's solve this. Add these guys together. 0x, 0y equals 0. What? Well, what happened here? One thing we can note is that 0 equals 0 is a true statement. This is in fact true. So we don't have parallel lines which would come up with the false statement. It would be there is no solution. 0 is equal to true. We do have a true equation. However, it's not very useful. Maybe we can do something going back and looking at our equations to figure out what's going on here. Well, let's look at the first equation. 5x minus 20y equals negative 40. I'm going to divide that equation by negative 5. I'm going to divide every coefficient by actually just 5. Let's just divide it by 5. And so if I take 5 divided by 5, I get x. 20 divided by 5, I get 4. Negative 40 divided by 5, I get negative 8. So what you can see is if I divide that first equation by negative 5, I end up with my second equation. In fact, if you look down here, if I had multiplied by 5, I would have got the exact same equation. So what happened is these guys are the same equation, right? These guys are the same equation. And if you graph them using Desmos or by hand, you would be graphing the exact same line. So this is our dependent system that we talked about. And any point on this line is a solution. So the way we write the solution to this equation is I had to take one of the equations and I solve it for y equals. So let's take x minus 4y equals negative 8, and we're going to solve this for y. Subtract x from each side, and we get minus 4y equals minus x minus 8. Divide everything by negative 4. And we get y equals 1/4 x plus 2. So the way I write this solution is I pick any constant c for x. And no matter what I pick for x, I can compute y to be 1/4 that constant plus 2. And this is what you write for your solution. Any point of the form c 1/4 c plus 2 is going to be a solution. That's the way we write solutions for dependent systems. All right, let's stop there.